All right, settle down, settle down. Let's get started. You know, I was walking across campus this morning enjoying the sunshine. It's a beautiful day in Pasadena, isn't it? And I started thinking about the questions people ask me. Not the big questions, not the ones about quantum electrodynamics or the specific spin of a meson. No, I mean the questions that children ask. The silly question. There is a terrible habit in our education system, a really dangerous habit of teaching people that some questions are too simple to be worth a scientist's time. We get so busy with our fancy equations and our big words that we forget how to look at the world. We stop asking why because we are afraid of looking stupid. But I'm going to tell you something. Looking stupid is the most important part of being a physicist. If you aren't confused, you aren't paying attention. So I want to talk about something today that seems painfully simple. It's something you see every single morning when you wake up and drag yourself into the bathroom to brush your teeth. You look in the mirror, and what do you see? You see yourself. But it's not you, is it? It's a copy. And there is something very strange about this copy. Look at this gentleman in the front row here, you with the blue sweater. If you raise your right hand, the fellow in the mirror raises his hand. But which hand is it? It's on the left side of his body. To him, it's a left hand. If you wink your right eye, the mirror, you winks his left eye. We say the mirror flips things, it reverses them, it swaps left and right. Now here is the question that is going to drive you crazy if you actually let yourself think about it. Why does the mirror flip left and right, but it doesn't flip up and down? Think about it. Your head is still at the top. Your feet are still at the bottom. The mirror didn't take your shoes and put them on your ears. It respected gravity. It kept up and down as down. But it took left and turned it into right. Why? Is the mirror smart? Does the glass know that gravity goes one way, so it better not mess with that axis? But it figures left and right a fair game. How does a piece of glass with a little bit of silver painted on the back know which way is up? I'll tell you right now, the answer is not in the math book. Well, it is. But it's hidden behind a lot of fancy notation that makes you feel smart but doesn't help you understand a thing. We are going to figure it out right here, just using our heads. We are going to find out that the mirror is doing something much more violent, much more profound than just swapping hands. First, we have to make sure we aren't fooling ourselves. That is the first principle of science. You must not fool yourself. And you are the easiest person to fool. Is it true that a mirror always flips left and right? Let's do an experiment. That's what we do. We don't just sit in armchairs and talk philosophy. We check. Imagine I take a mirror, a nice big one, and I lay it flat on the floor, right here in front of the desk. Now, I walk up to it and I stand on the edge looking down. What do I see? I see my own shoes, touching the shoes of the reflection. And where is the reflection's head? It's way down there pointing away from me. If I wave my hand, the reflection waves its hand. But look at the orientation. The reflection is upside down. So a wall mirror flips left and right. A floor mirror flips up and down. Now we are really in trouble. Because a mirror is just a mirror. It's the same piece of glass. It doesn't have a gyroscope inside. It doesn't know if it's on the wall or on the floor. The laws of physics that govern how light bounces off that silver backing are exactly the same in both cases. Light hits, light bounces. The angle in equals the angle out. That's it. That's the whole rule book. So if the laws are the same, why does the result look so different? Why does one orientation mess with our hands and the other mess with our heads? The answer, and this is where things get interesting, is that the mirror isn't doing either of those things. The mirror doesn't know what left is. It doesn't know what right is. And it certainly doesn't care about up. Left and right are not properties of the universe. They are properties of us. They are biological labels we stick onto the world. Because we happen to be built with 2 hands and 2 feet. If you were a spherical blob of jelly floating in deep space, left and right wouldn't mean a thing to you. We need to strip away these human words. We need a way to talk about space that doesn't depend on which way our noses are pointing. We need a system. Now, don't get scared. I'm not going to write a bunch of calculus on the board just yet. I want you to use your imagination. That's the best laboratory you have. Imagine 3 arrows, just 3 straight sticks. We are going to stick these arrows right through you. I know, it sounds painful, but it's for science, so bear with me. First we take an arrow and we shoot it straight up through your feet and out the top of your head. We'll call that the up-down arrow. Second, we take an arrow and shoot it straight through your hips, sticking out to your left and your right. We'll call that the left-right arrow. And third, this is the important one, so watch closely. We take an arrow and we shoot it straight out of your belly button, pointing forward, and out of your back, pointing backward. We'll call this the front-back arrow. So there you are, standing in front of the bathroom mirror, looking like a pincushion with these 3 arrows sticking out of you. Let's look at the reflection of these arrows. This is where we catch the mirror in the act. Look at the up-down arrow. The real one points to the ceiling. Look at the reflection. It also points to the ceiling. The head of the reflection is up. The feet are down. So the mirror did nothing to the vertical axis. It left it alone. Now, look at the left-right arrow. The one going through your real right hip is on the right side of the room, let's say, toward the bathtub. Look at the reflection. Its right hip is also on the side of the bathtub. The arrow points in the same direction. Wait a minute. Did you hear what I just said? Check it again. If you point your finger to the east, the reflection points its finger to the east. It doesn't point west. If you hold a ruler horizontally, the reflection holds the ruler horizontally. The mirror does not flip the left-right axis. The geometric line running from one side of the room to the other is preserved perfectly. So the up-down arrow is fine. The left-right arrow is fine. But we still have one arrow left. The belly button arrow. The front-back one. Look at that arrow on your real body. It is pointing straight at the mirror. It is pointing north, let's say. Now, look at the reflection. Which way is its arrow pointing? It's pointing at you. It's pointing south. Aha! We found it. The real arrow points forward. The reflected arrow points backward. The mirror didn't flip left and right. It didn't flip up and down. It flipped front and back. This is the secret. A mirror is a device for reversing depth. It turns the universe inside out along the direction you are looking. It squashes the world flat and pulls it back out the other way. Think about it like this. Imagine you have a rubber glove, a nice flexible gardening glove. You put it on your right hand. Now, imagine you could grab the wrist of that glove and pull it inside out. You pull the fingers through the wrist until the whole thing is reversed. If you put that inside out glove on a table, it won't fit your right hand anymore. It will look exactly like a left-handed glove. Did you magically turn right into left? In a way, yes. But how did you do it? You didn't rotate it. You pulled the front through the back. You inverted the depth. That is exactly what the mirror is doing to light. When a particle of light, a photon, leaves the tip of your nose, it travels forward to the mirror. It hits the glass and bounces straight back. A photon leaving your ear, which is further back than your nose, travels a little longer, hits the glass, and bounces back. The image of your nose is formed closer to the surface. The image of your ears is formed deeper in the reflection. The relationship of front to back is reversed relative to the direction of travel. So scientifically speaking, physically speaking, there is no left-right flip. That is a lie. There is a front-back flip. We call this a z-axis inversion, if we want to sound like mathematicians. But this creates a new problem, a psychology problem. If the physics is so simple, just a depth flip, why does my brain scream left-right reversal? Why do I look at that guy in the mirror and instinctively feel that he has swapped sides? Why don't I look at him and say, oh look, a creature that has been turned inside out like a sock? The reason is that you are a human being, and human beings are obsessed with symmetry. Let's look at your body again. You are roughly symmetrical left. Your left ear looks a lot like your right ear. Your left arm is built just like your right arm, just flipped. But you are not symmetrical front to back. Your nose looks nothing like the back of your head. Your chest looks nothing like your spine. And you are not symmetrical up to down. Your head is a bowling ball of bone with eyes in it. And your feet are flat plates for walking. Because we are bilaterally symmetrical, that means the left side matches the right side. Our brains have a very specific way of processing other people. When we see a person facing us, we don't think, oh, that is a front-back inverted human. That's too complicated. That's horrifying. A front-back inverted human would have their heart beating on the right side, their liver on the left. Well, actually, that's exactly what the reflection had. But we don't think about internal organs. We think about social interactions. When you see someone facing you, how did they get there? Usually they walked up and turned around. They rotated. If I stand next to you, facing the same way, and I want to look at you, I turn my body, I rotate 180 degrees. Now think about what happens when I rotate. If I spin around to face you, my right hand, which was on your right side, swings around and ends up on your left side. My left hand swings around to your right side. Rotation swaps left and right. This is deeply wired into our brains. We are used to things rotating. We see it every day. Doors rotate, wheels rotate, people rotate. We are not used to things turning inside out. We almost never see a z-axis inversion in nature. You don't see a dog walk down the street and suddenly turn inside out. That doesn't happen. So when you look in the mirror, your brain is faced with a choice. It sees a person who looks just like you. Hypothesis A. This is a creature that has been squashed flat and pulled inside out along the z-axis, reversing its depth. Hypothesis B. This is a creature that walked around behind the glass and rotated. Your brain, being a lazy but brilliant machine, picks hypothesis B every single time. It assumes the person in the mirror rotated to face you. And because it assumes rotation, it expects the hands to be swapped. If I rotate to face you, my right hand is across from your left. But the mirror didn't rotate, it inverted. So you look at the hand that is physically across from your right hand. Your brain says if he rotated, that should be his left hand. And the mirror says here is the image of the hand on the right. And your brain goes, oh, he is holding up his left hand. The confusion comes from the conflict between what the physics is doing, inversion, and what your intuition is expecting, rotation. You are trying to interpret a reflection as a rotation, and they are not the same thing. This is why the up-down question confuses us. Why doesn't the brain think the reflection stood on its head? Well, think about it. How often do you meet people who walk up to you and do a handstand to say hello? Almost never. Gravity is the boss. Gravity defines our world. Up and down are absolute directions for us. We don't mess with them. We rarely rotate around our waists. We almost always rotate around our vertical axis, our spine, like a spinning top. Because we live on a flat ground, with gravity pulling down, our mental model of turning around is always a horizontal rotation. We walk around each other. We don't flip over each other. So your brain doesn't even consider the possibility that the mirror guy flipped upside down. It only considers the horizontal rotation. And because the horizontal rotation implies a left-right swap, that is what you perceive. Now I can prove to you that this is all in your head. I can prove that left and right are just ideas you are projecting onto the glass. I want you to imagine you are writing a letter. You take a piece of clear plastic, like a transparency sheet, and you write the word Feynman on it with a thick black marker. Hold it up in front of you. You can read it perfectly. Feynman. Now hold it up to the mirror. What do you see? You see the letters flipped. The F is backwards. The E is backwards. It looks like secret code. Aha, you say. See, Feynman. The mirror flipped it left to right. The F is pointing the wrong way. But wait. Stop. Look at the piece of plastic in your hand. You are holding it so you can read it. That means the ink is on the side facing you. The back of the plastic is facing the mirror. The mirror is showing you the back of the plastic sheet. If you took that plastic sheet and simply turned it around to show it to a real person standing in front of you, what would you do? You would flip it over. You would rotate it. And when you rotate it, the F points the other way but the mirror lets you see the front of the letters, from your perspective, reflected back. Actually, let's try something even trickier. Take that plastic sheet, hold it so you can read it. Now instead of flipping it side to side, I want you to flip it top to bottom, turn it upside down. Now the F is upside down. Hold that to the mirror. The reflection is upside down. If you flip the object upside down, the mirror shows it upside down. If you flip the object left-right, the mirror shows it left-right. The mirror is just a tattletale. It just shows you exactly what is presenting to it. It is absolutely faithful. It doesn't interpret. You interpret. But this brings us to something much deeper, much more fundamental than bathroom mirrors and plastic sheets. We have been talking about symmetry. Symmetry is a word.
physicists use when we mean things stay the same even if you do something to them. A sphere is symmetrical, because if you rotate it, it looks the same. A picket fence is symmetrical. If you shift it over by one picket, it looks the same. For a long, long time, centuries really, physicists believed that the universe itself was symmetrical in a mirror. We call this parity. The idea was this: suppose you build a complicated machine, a clock, or an engine, or an atom smash, and you build it with every screw, every wire, every gear exactly in place. Now suppose you build a second machine that is the perfect mirror image of the first one. Everywhere the first machine has a screw on the right, the second has a screw on the left. It is a left-handed version of the machine. The question is, will the second machine run? And if it runs, will it run exactly the same way as the first one? Common sense screams yes. Why shouldn't it? Space is just space. Left, right, who cares? The laws of physics shouldn't care if you build a car with the steering wheel on the left or the right. The engine still burns gas. The wheels still turn. If I throw a ball with my right hand, the parabolic arc it makes is governed by Newton's. If I throw it with my left hand, the mirror image throw it follows the exact same parabolic arc, just mirrored. Newton's laws don't change. So we thought, okay, nature is blind to handedness. Parity is conserved. It seemed beautiful. It seemed right. It seemed like the universe was fair. But nature has a wicked sense of humor. In the 1950s, we started looking really closely at the smallest things in the universe. Not clocks, not cars, but particles. Specifically, the weak force. The force that causes radioactive decay. The thing that makes a Geiger counter click. And we asked the question again: if we take a radioactive atom that spins and shoots out an electron, and we look at it in a mirror, does the mirror image represent something that can actually happen in our universe? And to our absolute shock, the answer was no. The mirror lied. We found out that, for certain interactions, the universe is left-handed or right-handed, depending on how you define it. There are processes, real physical processes happening in the sun and in nuclear reactors where if you built the mirror image it would not work. The mirror machine would be broken. It was as if you looked in the bathroom mirror and your reflection dropped the toothbrush, even though you were still holding it. This discovery, parity violation, shook the foundations of physics. It meant that left and right aren't just human labels. At the deepest level of reality, the universe actually knows the difference. There is an intrinsic handedness to the fabric of reality. Think about that for a second. We started with a silly question about why your hair is parted on the wrong side in the glass. We used some simple arrows, right, up, forward, to show that the mirror is just flipping depth. We realized our brains are tricking us, because we are addicted to horizontal rotation. But if you dig deep enough into any silly question, you hit the bedrock of the universe. We found out that while a household mirror is just flipping the z-axis, the mirror of nature is cracked. Perfect symmetry is a myth. We live in a lopsided universe, and that is a good thing. If the universe were perfectly symmetrical, perfectly balanced in every way, maybe we wouldn't be here. Maybe matter and antimatter would have just cancelled each other out in the beginning, leaving nothing but light. A perfectly symmetrical universe might be a boring, empty place. The fact that the mirror breaks, that there is a little twist, a little imperfection in the law, that might be the only reason we exist, to ask these questions. Now I want to take this idea of coordinate transformation, that's the fancy name for our three arrows, and I want to push it a little further, because understanding the mirror isn't just about optics, it's about relativity. It's about how different observers see the same event. When you look in the mirror, you are an observer, looking at a virtual world. But what if you could step into the mirror? Alice went through the looking glass, right? And she found a world that was all backward. If you could step through the mirror into that room that looks just like yours, you would find that you didn't fit. If you tried to shake hands with your reflection, your right hand would meet his left hand. The grip would feel wrong. Your thumb would be on the wrong side. If you tried to read a book in the mirror world, you would have to learn to read backwards. But would you feel different? If you were born in the mirror world, grew up there, learned physics there, would you know you were in the wrong version? If you did chemistry in the mirror world, your sugar would taste different. Did you know that sugar molecules have a handedness? Dextrose and levulose, right-handed sugar and left-handed sugar. They are chemically identical in terms of atoms. Same carbon, same hydrogen, same oxygen, but they are mirror images, and your body, which is made of left-handed amino acids, can digest one but not the other. So if you stepped into the mirror world, you might starve to death while eating a full meal because your body wouldn't have the right key to unlock the energy in the mirror food. It's amazing, isn't it? A simple reflection reveals that biology, chemistry, and physics are all locked into this game of geometry. So let's recap what we've done so far before we take a break and get some coffee. We asked why mirrors flip left-right but not up-down. We found out that's a false accusation. Mirrors don't flip left-right, they flip front to back. They invert the depth. We found out that we think it's a left-right flip because we are mentally rotating ourselves to step into the mirror, and rotation swaps sides. Our brains choose the social explanation rotation over the geometric explanation inversion. And we found out that this matters because nature itself has a preference. But there is one more thing I want to leave you with before we move on. It's about the concept of information. When you look at the mirror, the light that reaches your eye carries information about the object. It carries color, intensity, and direction. But does it carry truth? We tend to think that seeing is believing. If I see it, it's there. But the mirror teaches us that seeing is interpreting. Your brain is constantly editing the raw data coming in from your eyes. It flips images. It fills in blind spots. It assumes symmetries that aren't there. Physics is the struggle to stop editing. It is the discipline of trying to see the raw field. When we write down an equation, like F(E)μ or the wave equation for light, we are trying to write down something that doesn't depend on whether you are looking in a mirror, or standing on your head, or spinning in a circle. We are looking for the invariant, the things that stay true no matter how you look at them. The mirror image changes, left becomes right, front becomes back, but the laws that govern the light bouncing, those are invariant, and that is what we are hunting for. We are hunting for the rules that don't care about our point of view. So the next time you brush your teeth, don't just check your hair. Look at that guy in the glass. Wink at him. Watch him wink back with the wrong eye. And remind yourself, I am looking at a z-axis inversion. And if anyone asks you why you're staring so intensely at yourself, just tell them you're doing high-energy physics in the bathroom. Alright, that's a good place to pause. When we come back, I want to talk about what happens when we start moving. Because if you think mirrors are confusing when you're standing still, just wait until we start running near the speed of light. That's when the real fun begins. Take 10 minutes. Go get some air. Alright, are we all back? Good. Did you get your coffee? I hope it was hot. You know, heat is just atoms jiggling around, but that's a lecture for another day. Before the break, we were talking about the bathroom mirror, the flat mirror, the one that tells you the truth about the z-axis, but lies to your brain about your hand. We decided that the left-right flip is a psychological trick, a result of our biological symmetry and our obsession with horizontal rotation. But I promised you that we were going to go deeper. We are going to leave the bathroom now. We are going to step out into a world where the mirrors aren't flat, and where the things being reflected aren't just faces, but time itself. I want you to imagine a different kind of mirror. Imagine you are at the carnival. You know, the fun house. They have those wavy mirrors. Some make you look short and fat. Some make you look tall and skinny like a piece of spaghetti. When you look at a flat mirror, we said the rule was simple. What goes in comes straight back. It's a one-to-one map, a linear map. If I move my hand 1 inch to the right, the reflection moves 1 inch to the right. It's predictable. But a curved mirror, that is where the calculus comes in. Calculus is a scary word for a lot of people. They hear it and they think of headaches and tests. But calculus is just the study of things that are changing. In a flat mirror, the slope of the glass never changes. It's always zero. It's flat. In a curved mirror, the slope, the angle of the glass is different at every single point. If you look at the top, the glass might be tilting down. If you look at the bottom, it might be tilting up. So when light hits the top, it bounces down. When it hits the bottom, it bounces up. If you curve the mirror enough like a spoon, something incredible happens. The light rays from your head bounce down, and the light rays from your chin bounce up, and somewhere in the middle, they cross. They cross paths, and once they cross, the top is at the bottom, and the bottom is at the top. Pick up a shiny spoon when you get home. Look at the back of it, the bump side. You look small and funny, but you are right side up. That's a convex mirror. It pushes the light out, it spreads the world apart. Now turn the spoon over. Look into the bowl, the concave side. If you are close, you look huge, but move the spoon away. Keep moving it. Suddenly, pop, you flip upside down. Why? Because you passed the focal point. You passed the point where the light rays crossed. This is a real flip. This isn't a psychological trick like the left-right business. The light rays literally changed places. The information that was on top is now physically located at the bottom. And this is what I mean when I say nature is playing a game of maps. A mirror is just a map. It takes the real world and maps it onto a reflected world. Sometimes the map is simple. Sometimes the map twists and turns. In physics, we deal with fields. Electric fields, magnetic fields, gravitational fields. These are just maps of invisible forces in space, and sometimes these fields get twisted. Think about a black hole. A black hole is like the ultimate funhouse mirror. It curves space so much that light can't even bounce back. It's a mirror that swallows the image. If you looked at a black hole, you wouldn't see a reflection. You would see a hole in the universe. But let's not get sucked into a black hole just yet. I want to talk about a different kind of reflection. I want to talk about the time mirror. We talked about symmetry in space, left versus right. But what about past versus future? Is time a mirror? Imagine I have a movie projector. I film a planet going around the sun. It's a beautiful image. Gravity is pulling it, momentum is pushing it. Now I take that film and I run it backward. What do you see? You see a planet going around the sun in the opposite direction. Does it look wrong? If you showed that backward movie to a brilliant astronomer, would he jump up and shout, "That's impossible"? No, he wouldn't. Because the laws of gravity work exactly the same way forward and backward. Gravity doesn't care about time. If you push a planet one way, it orbits. If you push it the other way, it orbits. The equation for gravity, the equation for mechanics, they are time reversible. They are symmetric in time. If you look at the fundamental laws of motion in a time mirror, the reflection looks perfect. You can't tell the difference between the past and the future just by looking at the planets. But, oops, I dropped my chalk. It broke into 3 pieces. Now imagine we film that. We film the chalk falling, hitting the floor and shattering. Run that film backward. On the screen you see 3 pieces of white dust jump off the floor, fly together, fuse into a solid stick, and leap into my hand. Now if you show that movie to anyone, even a child, they will say, "That's fake, that's magic, that's backwards." Why? If the laws of atoms bumping into each other are time reversible, and they are, why is the big picture not reversible? If I look at the atoms of the chalk, they are just bouncing. If I reverse the film, they are just bouncing the other way. That's a So why doesn't the chalk ever jump back into my hand? This is the problem of the arrow of time. It's the one mirror that seems to be smashed. You can go left, you can go right, you can go up, you can go down, but you can only go forward in time. You can never go back. This leads us to a concept called entropy. It's not a law of motion, it's a law of probability, it's a law of luck. There is only one way for the chalk to be a nice smooth stick. There are a billion ways for it to be a pile of dust. When things move forward in time, they tend to get messy. They tend to explore all those billion possibilities. They get lost in the disorder. To go backward, to fix the chalk, nature would have to get incredibly lucky. It would have to accidentally find that one arrangement out of a billion that looks like a stick. It's not impossible. Strictly speaking, it is not forbidden by the laws of physics for the floor to suddenly heat up, kick the chalk dust into the air and weld it back together.
It could happen, but don't wait around for it. You'd have to wait longer than the age of the universe. So the time mirror is a strange one. On the micro scale, the tiny scale of atoms, it works perfectly. Atoms bounce forward and backward the same. But on the macro scale, our scale, the mirror is dark. We can't see the past. We can't go back. But, and there is always a but in this class. What if I told you there is a way to cheat? What if I told you that there are particles that seem to move backward in time? Let's go back to our fundamental particles. Electrons. An electron is a little bundle of negative charge. It flies through space. Now suppose I make a mathematical graph. Time is on the vertical axis going up. Space is on the horizontal axis. An electron moving forward in time is a line going up and to the right. Now what if I draw a line going down? Mathematically, that represents an electron moving backward in time. What would that look like to us sitting here in the lab with our forward-moving watches? If you do the math, and this was something that puzzled us for a long time, an electron moving backward in time behaves exactly, and I mean exactly, like a particle with the opposite charge moving forward in time. An electron has a negative charge. If you reverse the time, it looks like it has a positive charge. Do we see particles like that? Positive electrons, yes. We call them positrons. Antimatter. This is a beautiful idea. It breaks your brain if you think about it too hard. When we see a positron, a piece of antimatter sitting in a cloud chamber, we usually say, oh look, a particle just like an electron but positive. But you could also say, look, that's an electron that is traveling backward in time. It's the same thing. The math doesn't care which description you use. This gives us a new kind of mirror, a space-time charge mirror. Remember, in the first half I told you about the parity mirror P, the one that swaps left and right, and I told you it was broken, that the universe is left-handed. Well, what if we combine mirrors? Imagine a machine that does three things to a particle. C, charge conjugation. It swaps matter for antimatter, plus becomes minus. P, parity. It flips it in a mirror, left becomes right. T, time reversal. It runs the movie backward. We call this the CPT theorem. And as far as we know, and we have checked this very, very carefully, this mirror is perfect. If you take the entire universe, every atom, every star, every galaxy, and you turn all the matter into antimatter and you flip everything left to right and you run time backward, that reflected universe would behave exactly like ours. It would follow the same law. So maybe the mirror isn't broken after all. Maybe we were just looking at a small piece of it. We were just looking at the left-right piece and complaining that it didn't work. We needed to look at the whole picture. The symmetries of charge, time, and space are locked together. You can't mess with one without messing with the others. This suggests that antimatter is just matter reflected in a very special kind of mirror. Now I want to show you one last trick. One last way to break your intuition about rotation and mirror. We talked about how your brain thinks the image in the mirror rotated to face you. And we said that a 80-degree rotation swaps left and right. We assume that if you rotate something 360 degrees, a full circle, it comes back to where it started. If I stand here and I spin around 360 degrees, I am facing you again. I look the same. I am the same, right? Well, not always. In the quantum world, there are things, particles like electrons, that have a property called spin. Now, spin is a terrible word. It makes you think of a top spinning on a table. Electrons aren't little tops. If they were spinning as fast as the math says, their surfaces would be moving faster than the speed of light, which is impossible. So spin is just a label we use for intrinsic angular momentum. It's just a property they have like mass or charge. But here is the weird part. If you take an electron and you rotate it 360 degrees, it does not come back to its original state. It comes back as the negative of itself. The wave function, the mathematical description of the electron, flips its sign. It's upside down. To get the electron back to exactly how it started, you have to rotate it another 360 degrees. You have to rotate it 720 degrees, 2 full circles, to get back to 1. Does that sound crazy? How can a full circle not bring you back home? I can show you. I can show you right now with a coffee cup. Do you have a cup? Or just use your hand? Hold your hand out in front of you, palm up, like you are holding a tray of drinks. Now I want you to rotate your hand in a circle, bringing it toward your body, under your armpit, and back out. Don't drop the imaginary drinks. Keep the palm up. If you do a 360-degree turn, your arm is twisted.
Your elbow is up in the air, you are in a knot. You are facing the right way, but you are not in the same state. You are under tension. Now keep going. Don't stop. Rotate another 360 degrees, bring your hand over your head, and back down to the front. Ah! Now your arm is straight again. The tension is gone. The knot is untied. It took 2 full rotations, 720 degrees to get your arm back to the zero state. Your arm is acting like a spinor. That's the math word for it. It's an object that lives in a world where 360 degrees isn't the whole story. The electron is like that. It is connected to the universe in a way that requires a double turn to untangle. Why am I telling you this? Because it shows us that our intuition about space, simple, flat, Euclidean space, where circles are circles and mirrors are mirrors, is just an approximation. It's a good enough model for building houses and throwing baseballs. But when you look closer, space is filled with hidden connections. It has topology, it has twists, it has symmetries that link time to antimatter and rotation to mathematical sign. We started this morning asking why the mirror flips your hand. We found out it doesn't flip your hand, it inverts your depth. We found out your brain lies to you because it prefers rotation. We found out that real rotation is stranger than we thought. And we found out that the ultimate mirror involves reversing time and charge, not just space. So what is the lesson? The lesson is that the world is a lot deeper than it looks. When you see a reflection, you are seeing a challenge. Nature is daring you to figure out the rule. She shows you a puzzle, a left hand that should be a right hand, and she waits to see if you will just accept it, or if you will ask why. Science is the process of not accepting the obvious answer. The obvious answer is mirrors flip left and right. The true answer involves geometry, psychology, group theory, and particle physics. The obvious answer is time flows forward. The true answer involves entropy and probability. I hope the next time you look in a mirror you don't just see your face. I hope you see the incredible, twisted, beautiful machinery of the universe staring back at you. And I hope you wink, just to see if the other guy winks back with the wrong eye. That's all for today. Go home, think about it, and don't break any mirrors. Not because of bad luck, but because you might accidentally create an antimatter universe in your bathroom. See you next week.